So the equation that we have there is that the voltage of the battery is equal to I because I had two resistors that were identical, right? Those two resistors are, we're going to say, they are in series, and this is the characteristic of a circuit in series. The two elements that are connected in series, the difference in potential of one plus the difference in potential of the other, they add up to the total difference in potential provided by the battery. So one of note before we move on to more complicated circuits and to parallel and so on. Let's take a few, think about a little bit about a few of the characteristics that we just encountered. First is that the voltage differences add up to zero, okay, that we said several times. The voltage across the resistors, if you're moving in the direction of the current, is going to be negative, minus I times R. That's the term that you're going to use to add in the sum of all of the differences in potential. Notice that in this kind of loop circuit, you have the same current everywhere, because there's only one path that the current can follow. Right? If this is R1 and this is R2, the fact that the current through R1 and R2 was the same had nothing to do with the fact that the resistances in this example that I just discussed were the same. Has nothing to do with that. The current just simply has to be the same along that path. It would be different if I had something else, some other path over here, or maybe actually in between them. Some other path over here, which would allow the current to go through one resistor, and then not all that current is going to have to go through the second resistor. It could go this way. So that would be a different situation. That would mean that the currents in both resistors are not the same. But that's, if it's a single loop, then the current, you can be sure that it's going to be the same. So think about what would happen if in the setup that we had with the light bulbs, so each one of these resistors was actually a light bulb. What would happen to that circuit if you unscrewed one of the light bulbs, removed one of the light bulbs from the circuit? So you're taking one of these out, and this is something that always confuses people in the exams. Because whenever there's a question about a light bulb in a circuit and the question says, now remove light bulb A, people are never sure, well, a lot of people are never sure what does that mean exactly, right? In terms of the circuit, in terms of the current and the resistors, resistance and so on. So this is what it means. If you remove a light bulb is simply a cable, then a little cable over here, and then another cable. It's a resistor, right? That thing in there is a resistor. So the current goes in one side, goes through the filament of the light bulb, and it comes out on the other side, right? So if I remove a light bulb, this is what you have. An open circuit, correct? So if there's an open circuit, of course, removing a light bulb means that your current has dropped to zero in that circuit. It means that the circuit is open. You can think of removing a light bulb as sort of replacing the resistor of the light bulb, which is small, with an infinite resistor. That will do the same job, right? If you put a resistor here that has a resistance equal to infinity, obviously current is not going to be able to flow through that resistor. Resistance is this difficulty that current has of going through a material. So if that difficulty is infinite, that means the current cannot go through from one side to the other. So a gap in the circuit is the same as a resistance equal infinite. Okay, so in your circuit, this is equivalent to, which is the same as saying that the resistance of that light bulb went to infinity, or the part of the circuit where the light bulb was goes to infinity. Removing a light bulb doesn't mean that the resistance at that part of the circuit went to zero. Okay, because nobody said that you removed the light bulb and you replaced it with something else, that you replaced it with a cable. Okay, if the problem says that you replaced it, then you're fine. But if the problem says remove light bulb A from your circuit, that happens to the current here and the voltage here and so on, this is not the situation that you have. That's not what it means. That would be the situation if the language had been connect a cable. You have your light bulb here. Sometimes the light bulbs are put an X inside. That's another typical notation for light bulbs. If the problem had said short the light bulb, connect the cable between the two sides of the resistor, or if it's a light bulb, then how does that affect the circuit? How does the resistance between, say, 0.1 and 0.2 change the moment you connect a cable between those 2 points? I haven't removed the light bulb. The light bulb is still there. And it has some resistance, whatever it is, finite number, 10 ohms, 20 ohms. But now you take an ideal cable and you connect it around that light bulb. What is the resistance between points 2 and points 1 and 2? Does it go to infinity? Does it go to 0? Does it go to some number? Is it still the same as the resistance of the light bulb? Say that the resistance of the light bulb was 10 ohms. There is no the ideal cable doesn't have any resistance, right? So if I apply Ohm's law to the ideal cable, right? Ohm's law is going to say that the difference in potential between the two sides of the cable, the ideal cable is connected between points 1 and point 2, so the difference in potential between point 1 and point 2 for that cable is going to be equal to minus the current that goes through that element multiplied by the resistance, right? I do know that the resistance of the cable is 0. So unless the current that goes through the cable is infinite, the product of the current and the resistance is going to have to be 0. To begin with, there's no infinite in the real world. So that is not a possibility. The current is going to have some finite number determined by the EMF of the battery and the resistor 2, the net resistance of that circuit, which is R2. And so the current is not 0. Therefore, the difference in potential between 1 and 2 must be 0 when you do that. So shorting, that is connecting a cable between the two sides of an element in a circuit, basically takes that element out without leaving the circuit open. It basically, what I'm saying that it takes it out is that it doesn't matter anymore. The current is not going to bother to go through that element if you just connect the cable from one side to the other. Just from Ohm's law. So that light bulb has been completely taken out of the circuit, effectively taken out, although not physically unscrewed from the circuit. Okay, we already discussed the situation when you take the light bulb out completely. So careful with those two situations. They are very different. One last comment about the circuit that we had before, which was this, okay, red, and we have VA. It went up for the battery, stayed constant, and it dropped in one resistor, then it dropped in the other one. Right, and this is point E, and this was point A. That red's a little too much. One last comment is, what would happen if I had actually had grounded point A? So this is the circuit that we have. This was point B, this was C, D, and E. What would happen if I grounded A? That means, if you remember, grounding is you take a cable, you connect it to whatever point you want, and that goes in contact with the ground, with the earth basically, which is a very big conductor. How would this plot change, and how would the slopes and everything else change if I were to do that? By definition, the voltage of the ground is 0, of the earth is 0, right? So if I connect point A with a cable to the earth, that cable is going to make sure that the voltage of point A and the earth are the same, because it's an ideal cable. So that immediately forces VA to be equal to 0. Does it affect the circuit in any other way? Does it affect the currents? The slopes in this plot? It doesn't do anything else. So if you were to plot the potential along this circuit, with the new condition that it's been grounded, then you would have to start with VA at 0. The battery would take the voltage 0 and bring it to the EMF of the battery, which would be, epsilon. Then between B and Z you would be flat again, because that's a conductor, cannot be a difference in potential there. It will drop because of the first resistor, and it will drop again because of the second resistor. And when you're back to E, your voltage should be back to 0, because the voltage of E and the voltage of A must be the same. We haven't changed that. There is still a cable connected between those 2 points. Okay? So that's how this plot would change if you were to ground A. But everything else will be the same. You just displace in this diagram. Now one more question about this. What would happen to this diagram? Again, this is point D here. If one of the resistors was smaller than the other one. Say that this is R1 and this is R2. In this diagram, R1 and R2 are the same, but now let's say that R1 is bigger than R2. How does this diagram change? How should I modify that diagram to incorporate that? The fact that R1 is bigger than R2. So this this point here is C, and this is E. This is B, and that's A. Let's talk about the things that won't change in that plot. What is not going to change? The potential at A and the potential at E must be the same, right? So the plot is going to have to go up, and then it's going to have to go down by the same amount, right? What else is not going to change? How high does the plot go? Does that change if I change the resistor too? That doesn't. Nobody said that the voltage of the battery was changing. If it was a real battery, it would probably have some internal resistance, so that would change things a little bit. But here we're just considering an ideal battery. So the EMF of the battery doesn't change just because you put a different resistor outside in the circuits, because you changed that. So the plot's still going up that way, starting from 0. It still goes to the same height, epsilon. It is flat between B and C. But how do the drops in R1 and R2, how do they change now? Which of those drops should be bigger than the other? What do those two resistors have in common? They have in common the current that is flowing through them. They both have the current I going through them, right? So the difference in potential between the across resistor 1 is going to be the current times R1. The difference in potential between across resistor 2 is going to be the current times R2. If R1 is bigger than R2, the difference in potential for resistor 1 is going to be bigger than the difference in potential for resistor 2. Right? So in that case, you would have a bigger drop here to D, and then the rest of it would be the drop to E. Right? And this difference is going to be the current times R1. And this difference here is the current times R2. Right? So that's how that graph would change.